Welcome to the episode of Biogeography program. A glacier is a persistent body of dense ice that is constantly moving under its own weight. It forms where the accumulation of snow exceeds its ablation over many years, often centuries. Glaciers slowly deform and flow due to stresses induced by their weight, creating crevasses, seracs, and other distinguishing features. They also abrade rock and debris from their substrate to create landforms such as cirques and moraines. Glaciers form only on land and are distinct from the much thinner sea ice and lake ice that form on the surface of bodies of water. On Earth, 99% of glacial ice is contained within vast ice sheets in the polar regions, but glaciers may be found in mountain ranges on every continent except Australia and on a few high altitude oceanic islands. Between 35° north and 35° south, glaciers occur only in the Himalayas, Andes, Rocky Mountains, a few high mountains in East Africa, Mexico, New Guinea, and on Zardku in Iran. Glacial ice is the largest reservoir of fresh water on Earth. Many glaciers from temperate, alpine and seasonal polar climates store water as ice during the colder seasons and release it later in the form of meltwater as warmer summer temperatures cause the glaciers to melt, creating a water source that is especially important for plants, animals and human uses when other sources may be scant. Within high altitude and Antarctic environments, the seasonal temperature difference is often not sufficient to release meltwater. Objectives of this lesson are to know about Quaternary glaciation or Pleistocene glaciation, causes of glaciation, ice ages of Earth's history, evidences for glaciation, effects of glaciation. Quaternary glaciation. An ice age is a period of long-term reduction in the temperature of the Earth's surface and atmosphere, resulting in the presence of expansion of continental and polar ice sheets and alpine glaciers. A glacial period, or alternatively glacial or glaciations, is an interval of time that is thousands of years within an ice age that is marked by colder temperatures and glacier advances. Interglacials, on the other hand, are periods of warmer climate between glacial periods. The last glacial period ended about 15,000 years ago. The Holocene epoch is the current interglacial. A time when there are no glaciers on Earth is considered a greenhouse climate change. Quaternary glaciation, also known as the Pleistocene glaciation or the current ice age, refers to a series of glacial events separated by interglacial events during the Quaternary period from 2.58 MA, that is million years ago, to present. During this period, ice sheets were established in Antarctica and perhaps Greenland, and fluctuating ice sheets occurs elsewhere. For example, the Laurentide ice sheet. The major effects of the ice age are erosion and deposition of material over large parts of the continents, modification of river systems, creation of millions of lakes, changes in sea level, development of pluvial lakes far from the ice margins, isostatic adjustment of the crust, and abnormal winds. It affects oceans, flooding, and biological communities. The ice sheets themselves, by raising the albedo, affect a major feedback on climate cooling. During the Quaternary period, the total volume of land ice, sea level, and global temperature has fluctuated initially on 41,000 and more recently on 100,000 year timescales, as evidenced most clearly by ice cores for the past 800,000 years and marine sediment cores for the earlier period. Over the past 740,000 years, there have been 8 glacial cycles. The entire Quaternary period starting 2.58 million years ago is referred to as an ice age because at least one permanent large ice sheet, Antarctica, has existed continuously. There is uncertainty over how much of Greenland was covered by ice during the previous and earlier interglacials. During the colder episodes referred to as glacial periods, large ice sheets also existed in Europe, North America and Siberia. The shorter and warmer intervals between glacials are referred to as interglacials. Currently, the Earth is in an interglacial period, which marked the beginning of the Holocene epoch. The current interglacial began between 10,000 and 15,000 years ago, which caused the ice sheets disappear from the last glacial period. Remnants of these lost glaciers, now occupying about 10% of the world's land surface, still exist in Greenland, Antarctica and mountainous region. The retreat of glaciers since 1850 is a consequence of the unequivocal warming of the climate system during the period. During the glacial periods, the present hydrologic system was completely interrupted throughout large areas of the world and was considerably modified in others. Due to the volume of ice on land, sea level was approximately 120 meters lower than present. The evidence of such glaciation in the recent past is robust. Over the last century, extensive field observations have provided evidence that continental glaciers covered large parts of Europe, North America and Siberia. Maps of glacial features were compiled after many years of fieldwork by hundreds of geologists who mapped the location and orientation of drumlins, eskers, moraines, striations and glacial stream channels. These maps revealed the extent of the ice sheets, the direction of flow and the locations of systems of meltwater channels, and they allowed scientists to decipher a history of multiple advances and retreats of the ice. Even before the theory of worldwide glaciation was generally accepted, many observers recognized that more than a single advance and retreat of the ice had occurred. Extensive evidence now shows that a number of periods of growth and retreat of continental glaciers occurred during the Ice Age, called glacials and interglacials. The interglacial periods of warm climate are represented by buried soil surfaces, peat beds and lake and stream deposits separating the unsorted, unstratified deposits of glacial debris. Causes of glaciation. No completely satisfactory theory has been proposed to account for Earth's history of glaciation. The cause of glaciation may be related to several simultaneously occurring factors such as astronomical cycles, atmospheric composition, plate tectonics and ocean currents. Astronomical cycles. The role of Earth's orbital changes in controlling climate was first advanced by James Krall in the late 19th century. Later, Milutin Milankovic, a Serbian geophysicist, elaborated on the theory and calculated these irregularities in Earth's orbit could cause the climatic cycles known as Milankovitch cycles. They are the result of the additive behavior of several types of cyclical changes in Earth's orbital properties. Changes in the orbital eccentricity of Earth occur on a cycle of about 100,000 years. The inclination or tilt of Earth's axis varies periodically between 22 degrees and 24.5 degrees. The tilt of Earth's axis is responsible for the seasons. The greater the tilt, the greater the contrast between summer and winter temperatures. Changes in the tilt occur in a cycle of 41,000 years long precession of the equinoxes or obols on Earth's spin axis, complete every 21,700 years. According to the Milankovitch theory, these factors cause a periodic cooling of Earth, with the coldest part in the cycle occurring about every 40,000 years. The main effect of the Milankovitch cycles is to change the contrast between the seasons, not the amount of solar heat Earth receives. These cycles within cycles predict that during maximum glacial advances, winter and summer temperatures are lower. The result is less ice melting than accumulating and glaciers build up. Milankovitch worked out the ideas of climatic cycles in the 1920s and 1930s, but it was not until the 1970s that sufficiently long and detailed chronology of the quaternary temperature changes was worked out to test the theory adequately. Studies of deep sea cores and the fossils contained in them indicate that the fluctuation of climate during the last few 100,000 years is remarkably close to that predicted by Milankovitch. A problem with the theory is that the astronomical cycles have been in existence for billions of years, but glaciation is a rare occurrence. Astronomical cycles correlate perfectly with glacial and interglacial periods and their transitions inside an ice age. Other factors such as the position of continents and the effects of this has on the Earth's oceanic currents or long-term fluctuations inside the core of the Sun must also be involved that caused Earth's temperature to drop below a critical threshold and thus initiate the ice age in the first place. Once that occurs, Milankovitch cycles will act to force the planet in and out of glacial periods. Atmospheric composition. One theory holds that decreases in atmospheric carbon dioxide, an important greenhouse gas, started the long-term cooling trend that eventually led to glaciation. Recent studies of the carbon dioxide content of gas bubbles preserved in the Greenland ice cores lend support to this idea. The geochemical cycle of carbon indicates more than a 90% decrease in atmospheric carbon dioxide since the middle of the Mesozoic era. An analysis of carbon dioxide reconstructions from Alkenon records shows that carbon dioxide in the atmosphere declined before and during Antarctic glaciation and supports a substantial carbon dioxide decrease as the primary cause of Antarctic glaciation. Carbon dioxide levels also play an important role in the transitions between interglacials and glacials. High carbon dioxide contents correspond to warm interglacial periods and low carbon dioxide to glacial periods. However, studies indicate that carbon dioxide may not be the primary cause of the interglacial glacial transitions, but instead acts as a feedback. The explanation for this observed carbon dioxide variation remains a difficult attribution problem. Plate tectonics and ocean currents. An important component in the long-term temperature drop may be related to the positions of the continents relative to the poles, but it cannot explain the rapid retreat and advances of glaciers. This relation can control the circulation of the oceans and the atmosphere, affecting how ocean currents carry heat to high latitude. Throughout most of the geologic time, the North Pole appears to have been in a broad, open ocean that allowed major ocean currents to move unabated. Equatorial waters flowed into the polar regions, warming them with water from the more temperate latitudes. This unrestricted circulation produced mild, uniform climates that persisted throughout most of geologic time. Throughout the Cenozoic era, the large North American and South American continental plates moved westward from the Eurasian plate. This drift culminated in the development of the Atlantic Ocean, trending north-south with the North Pole in the small, nearly landlocked basin of the Arctic Ocean. The Isthmus of Panama developed at a convergent plate margin about 3 million years ago and further separated oceanic circulation and created the Pacific and Atlantic Oceans. Ice ages of Earth's history. The presence of so much ice upon the continents had a profound effect upon almost every aspect of Earth's hydrologic system. The most obvious effects are the spectacular mountain scenery and other continental landscapes fashioned both by glacial erosion and deposition instead of running water. Entirely new landscapes covering millions of square kilometers were formed in a relatively short period of geologic time. In addition, the vast bodies of glacial ice affected the earth well beyond the glacier margins. Directly or indirectly, the effects of glaciation were felt in every part of the world. Glaciation has been a rare event in Earth's history, but there is evidence of widespread glaciation during the late Paleozoic era, that is 200 to 300 million years ago, and during late Precambrian, that is in the new Proterozoic era, that is 600 to 800 million years ago. Before the current ice age, which began 2 to 3 million years ago, Earth's climate was typically mild and uniform for long periods of time. This climatic history is implied by the types of fossil plants and animals and by the characteristics of sediments preserved in the atmospheric record. There are, however, widespread glacial deposits, recording several major periods of ancient glaciation in various parts of the geologic record. Such evidence suggests major periods of glaciation prior to the current Quaternary glaciation. The best documented record of pre-Quaternary glaciation, called the Karoo Ice Age, is found in the late Paleozoic rocks in South Africa, India, South America, Antarctica and Australia. Exposures of ancient glacial deposits are numerous in these areas. Deposits of even older glacial sediment exist on every continent except South America. These indicate that two other periods of widespread glaciation occurred during the late Precambrian, producing the snowball Earth during the Cryogenian period. There have been 5 known ice ages in the Earth's history, with the Earth experiencing the Quaternary Ice Age during the present time. The second ice age, and possibly most severe, is estimated to have occurred from 800 to 635 million years ago in the Neo-Proterozoic era, and it has been suggested that it produced a second snowball Earth in which the Earth iced over completely. It has been suggested also that the end of this second cold period was responsible for the subsequent Cambrian explosion, a time of rapid diversification of multi-cell life during the Cambrian period. A minor series of glaciations occurred from 460 million years to 430 million years ago. There were extensive glaciations from 350 to 250 million years ago. The current ice age, called the Quaternary glaciation, has seen more or less extensive glaciation on 40,000 and later 100,000 year cycles. Evidence for ice ages. There are 3 main types of evidence for ice ages. They are geological, chemical and paleontological. Geological evidence for ice ages comes in various forms, including rock scoring and scratching, glacial moraines, drumlins, valley cutting and the deposition of till or tillites and glacial erratic. Successive glaciations tend to distort and erase the geological evidence, making it difficult to interpret. Furthermore, this evidence was difficult to date exactly. Early theories assumed that the glacials were short compared to the long interglacials. The advent of sediment and ice cores revealed the true situation. Glacials are long, interglacials are short. It took some time for the current theory to be worked out. The chemical evidence mainly consists of variations in the ratios of isotopes in fossils present in sediments and sedimentary rocks and ocean sediment cores. For the most recent glacial periods, ice cores provide climate proxies from their ice and atmospheric samples from included bubbles of air. Because water containing heavier isotopes has a higher heat of evaporation, its proportion decreases with colder conditions. This allows a temperature record to be constructed. However, this evidence can be confounded by other factors recorded by isotopes ratios. The paleontological evidence consists of changes in the geographical distribution of fossils. During a glacial period, cold adapted organisms spread into lower latitudes, and organisms that prefer warmer conditions become extinct or are squeezed into lower latitudes. This evidence is also difficult to interpret because it requires sequences of sediments covering a long period of time over a wide range of latitudes and which are easily correlated. Ancient organisms which survive for several million years without change and whose temperature preferences are easily diagnosed, and the finding of the relevant fossils. Despite the difficulties, analysis of ice core and ocean sediment cores has shown periods of glacials and interglacials over the past few million years. These also confirm the linkage between ice ages and continental crust phenomena such as glacial moraines, drumlins, and glacial erratics. Hence, the continental crust phenomena are accepted as good evidence of earlier ice ages when they are found in layers created much earlier than the time range for which ice cores and ocean sediment cores are available. Effects of glaciation. Although the last glacial period ended more than 10,000 years ago, its effects can still be felt today. For example, the moving ice carved out of landscape in Canada, Greenland, northern Eurasia and Antarctica, the erratic boulders, till, drumlins, escarps, jords, kettle lakes, moraines, cirques, horns, etc. are typical features left behind by the glaciers. The weight of the ice sheets was so great that they deformed the Earth's crust and mantle. After the ice sheets melted, the ice covered and rebounded. Due to the high viscosity of the Earth's mantle, the flow of mantle rocks, which controls the rebound process, is very slow at a rate of about 1 cm per year near the center of rebound area today. During glaciation, water was taken from the oceans to form the ice at high latitudes. Thus, global sea level dropped by about 110 meters, exposing the continental shelves and forming land bridges between land masses for animals to migrate. During deglaciation, the melted ice water returned to the oceans, causing sea level to rise. This process can cause sudden shifts in coastlines and hydration systems, resulting in newly submerged lands, emerging lands, collapsed ice dams resulting in salination of lakes, new ice dams creating vast areas of fresh water, and a general alteration in regional weather patterns on a large but temporary scale. It can even cause temporary reglaciation. This type of chaotic pattern of rapidly changing land, ice, saltwater, and freshwater has been proposed as the likely model for the Baltic and Scandinavian regions, as well as much of Central North America at the end of the last glacial maximum, with the present day coastlines only being achieved in the last few millennia of prehistory. Also, the effect of elevation and Scandinavia submerged a vast continental plain that had existed under much of what is now the North Sea, connecting the British Isles to continental Europe. The redistribution of ice water on the surface of the earth and the flow of mantle rocks causes changes in the gravitational field as well as changes to the distribution of the moment of inertia of the earth. These changes to the moment of inertia result in a change in the angular velocity, axis and oval of the earth's rotation. The weight of the redistributed surface mass loaded the lithosphere caused it to flexure and also induce stress within the earth. The presence of the glaciers generally suppressed the movement of faults below. However, during deglaciation, the faults experience accelerated slip, triggering earthquakes. Earthquakes triggered near the ice margin may in turn accelerate ice calving and may account for the Heinrich events. As more ice is removed near the ice margin, more interplate earthquakes are induced, and this positive feedback may explain the fast collapse of ice sheets. In Europe, glacial erosion and isostatic sinking from weight of ice made the Baltic Sea, which before the Ice Age was all land drained by the Eridanos River. Ice cores are used to obtain a high resolution record of recent glaciation. It confirms the chronology of the marine isotopic stages. Ice core data shows that last 400,000 years have consisted of short interglacials, that is 10,000 to 30,000 years, about as warm as the present alternated with much longer 70,000 to 90,000 years, glacials substantially colder than present. The new Antarctic ice core has revealed that between 400,000 and 780,000 years ago, interglacials occupied a considerably larger proportion of each glacial interglacial cycle, but were not as warm as subsequent interglacials. Because glacial mass is affected by long-term climate changes, for example, precipitation, mean temperature, cloud cover and glacial mass changes are considered among the most sensitive indicators of climate change and are a major source of variations in sea level. Thank you.